August 4, 1944. The sky over Tinian burned with tracer fire. Lieutenant J.G. George W. Smith of VF-27, flying an F6F Hellcat from USS Princeton, CVL-23, had been strafing Japanese positions near Tinian town when his Pratt & Whitney R-2800 began coughing black smoke. A 13mm round had punctured his oil line. He tried to climb, but the temperature gauge spiked. The engine seized at 2,000 feet. Smith bailed out just offshore. Japanese soldiers dragged the dripping pilot from the shallows. His aircraft, remarkably intact, lay half buried in coral sand, a navy blue Hellcat with white stars still bright under Pacific sunlight. By nightfall, orders arrived from the Imperial Japanese Navy's 1st Air Technical Arsenal in Yokosaka. Recover the wreck. Priority, Class 1. It would be shipped, piece by piece, to Japan aboard a Nakajima G6N Lorna transport and 2 freighters under cover of darkness. The Allies had their radar. The Japanese wanted the next best thing, knowledge. 4 months, Japanese engineers had watched the Hellcat dominate the Pacific. Introduced in August 1943, it replaced the older F6F Wildcat. It was heavier, over 12,000 pounds loaded, but faster, tougher, and deadlier. Its 2,000 horsepower engine could push it to 380 miles per hour at 23,400 feet. 6.50 caliber M2 Browning machine guns spat 1,200 rounds per minute each. Against the A6M50, it was slaughter. At the Naval Air Technical Arsenal, engineers under Commander Eiichi Iwaya had one goal: decode the Hellcat's secrets. The captured aircraft, Hellcat Bureau number 70143, arrived at Yokosaka in September 1944. The fuselage was scarred but sound. Wings, propeller, and cowling bore bullet damage. The cockpit instruments were mostly intact. To the Japanese, it was a marvel of industrial power, a machine designed for mass production and battlefield repair, not delicacy. Iwaya's team began disassembly under heavy security. Cameras documented every bolt and bearing. They cataloged American materials: aluminum alloys, electrical wiring gauges, hydraulic seals, each measured, each logged. The engine, the Pratt & Whitney R-2800-10W double wasp, fascinated them most. It was a twin-row, 18-cylinder radial with a 2-stage, 2-speed supercharger. It delivered nearly 2,200 horsepower with water injection. Nothing in Japan's arsenal matched it. The engineers compared it to their own Nakajima NK9H HOM R21, 1,990 horsepower on paper, but in practice, overheating and power loss crippled it above 20,000 feet. The Hellcat's power plant ran smoother, cooler, and could be maintained by mechanics in forward bases. Its cowl flaps, ducting, and baffling were masterpieces of airflow control. They noted the armor: 212 pounds of steel around the cockpit, bulletproof windscreen, self-sealing fuel tanks. The Hellcat could take hits that would turn a zero into a fireball. American doctrine was clear: protect the pilot, not just the plane. Japan's doctrine, born from years of light, maneuverable fighters, had no answer. By October, the Hellcat had been fully stripped, measured, and reassembled in Yokosaka Hangar No. 4. Engineers ran bench tests on its instruments, its radio, its radar beacon. They even simulated catapult launches using a dummy carrier deck. Reports filled binders: performance charts, aerodynamic analysis, material breakdowns. But beneath the data lay a grim truth: Japan lacked the industrial base to replicate it. Their factories were running on fumes. Aluminum stocks were shrinking. Skilled labor had been drafted. Bombing raids had begun to tear at the heart of Tokyo's industry. Still, Iwaya persisted. He ordered a prototype program, the Type G carrier fighter, modeled on the Hellcat's lines but adapted for Japanese materials. It would never leave the drawing board. When engineers finally submitted their report to the Naval Air Headquarters in December 1944, one line stood out: technically feasible, strategically impossible. They had cracked the Hellcat, but realized they could not build one. And yet, the lessons would shape every aircraft Japan designed in its dying months. December 12, 1944. Yokosaka Naval Air Technical Arsenal. Inside Hangar No. 4, Commander Eiichi Iwaya stood before a whiteboard filled with blue chalk lines, cross-sections of the F6F Hellcat's fuselage. The engineers had spent 3 months translating those lines into Japanese measurements, redrawing American inches into millimeters. Every rib, spar, and bulkhead was now labeled in kanji. They called it Gokuhi Kikaku Gata G, Top Secret Project Type G. The idea was simple on paper: build a Japanese Hellcat using domestic resources. The reality was brutal. American engineering relied on precision machining and abundant alloys. Japan's factories by late 1944 were starved. Aluminum from Manchuria arrived irregularly. Copper was rationed. Tool steel for dies and jigs was gone. Tokyo's Nakajima Musashino plant had been bombed twice in November, halting most large engine production. Still, Iwaya's team began constructing sub-assemblies using scrap aluminum from damaged A6M0s. Their prototype frame weighed 9% more than the Hellcats, even before armor or equipment. Rivet spacing varied because Japanese riveting tools lacked the same pneumatic precision. Fuel tanks leaked under pressure. Hydraulic lines ruptured during vibration tests. In short, they could draw it but not make it. At the same time, the Imperial Japanese Navy's Aeronautical Department ordered comparative testing. The Hellcat's captured R-2800 engine was mounted on a dynamometer beside a Nakajima HOM R-21. At 44 inches of manifold pressure, the double Wasp produced 2,000 horsepower steady for 30 minutes without detonation. The HOM-R began misfiring after 5. Power to weight, cooling stability and compressor efficiency, all superior, the test log read. The Japanese supercharger design lagged by nearly a decade in metallurgy and tolerances. They lacked the high-octane fuel, US 100/130 grade, to sustain such pressures. Japanese aviation fuel rarely exceeded 87 octane. To close the gap, engineers proposed a hybrid, marry the Hellcat's aerodynamics with the Mitsubishi Mk9D engine, an 18-cylinder radial rated at 2,200 horsepower. They called the project A7M3J Replica. But Mitsubishi was crippled by bomb damage. The prototype never advanced beyond wooden mock-ups. Meanwhile, the Americans pressed their advantage. By January 1945, over 12,000 F6Fs had rolled off Grumman's assembly lines in Bethpage, New York, one every 63 minutes. Japanese intelligence knew the numbers. They were demoralizing. Their own monthly fighter output had fallen below 500 aircraft. The war had become arithmetic and Japan's columns didn't add up. Back at Yokosaka, Iwaya's engineers dissected another component, the Hellcat's radio and radar system. The AN/APS-6 radar, operating at 3 cm wavelength, could detect enemy aircraft up to 5 miles away. Japan's equivalent, the Type 3 Ku Mark 6, barely achieved half that range and was too bulky for single-seat fighters. The F6F's small, flush-mounted radome under the wing seemed almost like alien technology, compact, reliable, efficient. The more they learned, the more they saw the chasm between design philosophy and logistics. American engineers optimized for survivability and ease of repair. Japanese doctrine still prized agility and pilot skill. But by 1944, skill alone was being erased by radar, training programs and replacement rates. In February 1945, as B-29s began their nightly raids over Tokyo, the arsenal's power grid was hit. Blueprints burned. Records vanished. The half-completed prototype frame was evacuated to a tunnel near Nagano. It would never fly. Yet Iwaya's men refused to stop. They reduced what remained into a final document, Technical Analysis Report, Model F6F5. It contained 300 pages of schematics, metallurgical comparisons and aerodynamic data. Copies were hand-carried to the Naval Staff Office and the Yokohama Technical Bureau. One engineer scribbled a marginal note. This plane was not designed merely to win dogfights. It was designed to win wars. That insight, cold, precise, summed up everything Japan's aviation doctrine had missed. The Hellcat wasn't a masterpiece of artistry. It was a masterpiece of systems thinking. February 19, 1945. Iwo Jima. From the decks of USS Bunker Hill, CV-17, nearly 40 F-6F-5 Hellcats lifted into the ash-gray dawn. Their mission: secure air superiority before the Marines landed. Over Mount Suribachi, they met the last defenders of Japan's old doctrine, A6M50s of the 252nd Kokutai. The battle lasted 17 minutes. Radar directed from the carrier, Hellcats formed tight four-plane sections. Altitude advantage, 12,000 feet. Zeros climbed into the sun, the classic Tate-Wary maneuver. But radar and radio coordination made surprise impossible. Within 3 passes, 9 Zeros fell blazing into the surf. Not a single Hellcat was lost. American pilots were no longer hunting by instinct. They were executing systems. This was the collision Japan's engineers at Yokosaka had foreseen. The Hellcat's design wasn't just about horsepower, It embodied an entire operational philosophy: technology serving doctrine, doctrine serving production. Back in Japan, the air staff knew it too. Reports from the Philippines and the Marianas had been brutal. Between October 1944 and February 1945, Japan lost over 1,500 carrier-capable aircraft. The U.S. lost fewer than 250. Even worse, the Imperial Navy had no pipeline to replace its pilots. Training programs that once took 2 years were now 6 months, or less. Cadets learned gunnery on simulators made of plywood. The Hellcat's pilot school, in contrast, NAS Jacksonville, NAS Glenview, and NAS Miramar, graduated 1,200 new pilots each quarter, each trained with radar intercepts, carrier landings, and formation tactics drilled to perfection. Japan's air doctrine, still fixated on the dueling ace, was collapsing under the weight of American standardization. In March 1945, the Yokosaka team was summoned to brief Admiral Toyota Somu, Chief of the Naval General Staff. Commander Iwaya laid their technical charts on the table: lift coefficients, wing load ratios, engine output curves. But the Admiral wasn't interested in numbers. He asked only one question: can we build fighters that will win back the skies? Iwaya's reply was exact: no, Admiral. Not in time. Not in number. That was the end of the illusion. The staff minutes record Toyota's words: then we will fight with the pilots we have left. If they cannot win, they will die for Japan. 2 weeks later, the TACO Special Attack program expanded. Dozens of trainees were reassigned from advanced flight schools to kamikaze units. The first of these, the 601st Air Group, flew their final missions in April 1945. Young men, barely trained, in A6M5S stripped of guns to carry 250 kilograms bombs. The irony wasn't lost on Iwaya's engineers. They had spent months dissecting a fighter built to save its pilot, only to watch their nation build machines designed to kill him with certainty. At the same time, the Hellcat evolved again. The F6F-5N night fighter variant, equipped with the AN/APS-6 radar and flame dampeners, was deployed over Okinawa. On May 4, 1945, Lieutenant Commander Richard Harmer of VF-N-107 scored the first radar-guided kill of a Kamikaze Zero at 5,000 feet, without visual contact. The Japanese command never understood how they'd been spotted in the dark. Every technical advantage the Yokosaka team cataloged was now killing their own men. By late May, fuel reserves were nearly gone. Japan's total aviation fuel production for 1945 fell below 150,000 barrels, compared to America's 42 million. Training flights were cancelled. Aircraft were hidden under camouflage nets. The Yokosaka arsenal, once the center of technical innovation, was now a triage ward for burned-out engines and bombed-out frames. When B-29s firebombed Tokyo on March 9 to 10, 1945, the arsenal's hangar No. 4, home of the disassembled Hellcat, was incinerated. Only fragments survived: a warped propeller, half a wing spar, and a water-stained logbook of test results. The next morning, engineers stood among the ashes. No speeches. No ceremony. They knew what the wreckage meant: Japan's air war was finished. But Iwaya ordered one last effort: a complete technical digest of everything they'd learned. If Japan could not outbuild America, it would at least understand how America had won. That report would survive the war, and shock the Allied occupation teams who found it. August 2, 1945. Yokosaka Naval Technical Arsenal, 40 miles south of Tokyo. The war was already lost. The Americans had landed on Okinawa in April. Tokyo lay in ruins. Yet deep in a reinforced basement beneath Arsenal Building No. 12, engineers still worked. Commander Eiichi Iwaya supervised them personally. Their final task: to compile a definitive post-mortem on the F6F Hellcat, Japan's most studied enemy fighter. The document's title was Clinical: Analysis Report of Captured Enemy Aircraft, F6F-5 U.S. Navy Fighter. Volume, 326 pages. Classification, Gokuhi, Most Secret. 3 copies were made. Each hand-bound in gray cloth, each stamped with the Imperial Chrysanthemum seal. The opening section read like a confession. This aircraft represents the industrial and operational synthesis of the United States. Its superiority lies not in its maximum speed or climb rate, but in the integration of engineering, logistics, and pilot survivability. The report broke the Hellcat down to its atoms. Page 17, Engine Test Data, Pratt & Whitney R-2800-10W, 2-speed supercharger, critical altitude 23,400 feet, continuous power 1700 horsepower at 44 nhg. Page 41, propeller efficiency curve, Hamilton standard hydromatic, 13 feet 1 inch diameter, constant speed, 86% efficiency in climb. Page 62, armor layout diagram, 6 mm around cockpit sides, 38 mm behind the seat, 64 mm windscreen. Every number was logged, compared, and annotated against Japanese equivalents. HAMR 21, A6M50, N1K2J Shidenkai. The gaps were merciless. Section 3, Operational Philosophy. Here, Iwaya's engineers ventured into doctrine. They noted that the Hellcat was designed not for ace pilots, but for the average. The aircraft's stability in gunnery and recovery allows pilots of ordinary skill to achieve consistent results, one passage read. American design assumed pilot replacement. Japanese design assumed pilot irreplaceability. The data told the story. The Hellcat's kill ratio in the Pacific, 19-1. Japanese Navy Air Service loss ratio, 11-1 even against mixed Allied fighters. By 1945, Hellcats had destroyed over 5,100 enemy aircraft, more than any other Allied naval plane. Section 5, Industrial Considerations. This section was brutal in its honesty. American production methods emphasize standardization of subcomponents, modular repair, and accessibility. Japanese design prioritizes weight reduction and performance, but sacrifices interchangeability. They included a telling example. In a U.S. Navy forward depot, a Hellcat could have its engine replaced in 6 hours using standardized mounts and quick disconnect fittings. At Yokosaka, replacing an A6MS Sakai 21 engine required 3 days and often custom hand-fitting. They concluded, "Our airframes are works of craftsmanship. Theirs are products of systems." That phrase circulated through post-war circles for decades, a eulogy for Japan's wartime industry. The final section, Tactical Implications, distilled what the engineers had learned about combat dynamics. It cited engagement data from the Marianas, Leyte Gulf, and Okinawa. The Hellcat's ability to absorb hits, retain control, and outdive opponents was unparalleled. A surviving test pilot described it bluntly, "To shoot it down you must first catch it. You cannot." On August 6, 1945, 3 days after the report's completion, Hiroshima vanished beneath a single atomic blast. The engineers at Yokosaka heard the news in silence. By August 9, Nagasaki was gone. On August 15, Emperor Hirohito's voice, crackling through the radio, announced surrender. When U.S. occupation forces arrived at Yokosaka on August 30, they found the arsenal largely intact. Among the confiscated documents was Iwaya's report, stored in a steel cabinet wrapped in fireproof cloth. The Americans shipped it to the Naval Air Material Center in Philadelphia for translation. The first page of the translated summary stunned them. "We have found no technical deficiency in this aircraft. Its excellence is comprehensive." That sentence, from the enemy's own engineers, became a quiet badge of honor at Grumman Aircraft Engineering Corporation. Copies circulated among post-war design teams at Bethpage. A marginal note by a Grumman engineer simply read, "We built something they couldn't copy." In the ashes of Yokosaka, Commander Iwaya wrote one last entry in his personal logbook before the Americans took him into custody. "The war proved that courage without machinery is suicide. We built for heroes, they built for soldiers. History will favor the latter." It was the last line he ever wrote as an officer of the Imperial Japanese Navy. September 1945. Yokosaka Naval Base, now under the white-starred flag of the U.S. Navy. Commander Frank McIntyre, Technical Intelligence Unit, Pacific Fleet, walked through the rubble of the Naval Air Technical Arsenal. Smoke still drifted from the burned-out hangars. The Japanese technicians, now prisoners, stood in line under guard. McIntyre's orders were explicit. Collect every document, photograph, and piece of foreign technology. Within 48 hours, 20 trucks rolled out of Yokosaka bound for Atsugi Airfield, loaded with crates stamped enemy aviation material. Inside one of them sat 3 gray-bound volumes, the complete F6F analysis report. U.S. Naval Intelligence tagged it as Item 301A. The Americans had studied captured aircraft before, Zeros, Oscars, Tonys, but never like this. This was the enemy studying them. It was a mirror held up to their own engineering. The report was translated at the Naval Air Material Center in Philadelphia by December 1945. Engineers at Grumman and Pratt & Whitney received copies under restricted circulation. What they read astonished them. Page after page described the Hellcat with surgical precision. Performance envelopes, stress tolerances, heat dispersion under high manifold pressure, aerodynamic stall behavior at 140 knots. The Japanese analysis matched Grumman's own test data within 2%. Their instrumentation had been crude, but their minds relentless. Grumman's chief engineer, Gordon Israel, later wrote in a company memo, "They understood the airplane better than most of our pilots did." But what struck the Americans wasn't admiration, it was revelation. The report revealed how deeply Japan had misunderstood the system that created the Hellcat. The Japanese engineers assumed every part was the result of individual genius. They cataloged tolerances and alloys as if chasing a secret formula. What they missed was process. Mass production, modular tooling, statistical quality control. The very things invisible to microscopes. McIntyre's intelligence notes summarized it bluntly. They saw the airplane. They never saw the factory. In early 1946, Grumman invited representatives from the Navy Bureau of Aeronautics to discuss lessons from captured enemy research. Among the topics, ruggedization, modular repair, and pilot survivability, all design philosophies vindicated by the war's end. When the Hellcat's replacement, the F6F Bearcat, entered service later that year, its engineers referenced the Japanese report during final evaluations. The irony was absolute. Japan's analysis helped refine America's next fighter. Meanwhile, in Japan, the post-war purge dissolved the Imperial Navy. Commander Eiichi Iwaya was interrogated twice by U.S. intelligence. The transcripts, declassified decades later, reveal his calm precision. He explained that his team's work was not espionage but science, an autopsy of defeat. "We wanted to understand the difference between courage and capability," he told his interrogator. "We discovered that courage can be built if your industry allows it." The Americans took note. Iwaya was never charged with war crimes. By 1949, he was quietly consulting for Japan's new Aeronautical Research Institute under the Ministry of Education. His expertise, reverse engineering under scarcity, became invaluable in rebuilding Japan's post-war aerospace sector. Meanwhile, at Grumman's Bethpage plant, a framed copy of the translated report hung in the design office. On the bottom margin, an anonymous engineer had written, "Victory through repetition, not reinvention." The Hellcat's influence continued. Its lessons, stability, protection, manufacturability, formed the DNA of post-war U.S. naval aviation. The F-9F Panther, the Navy's first successful jet, owed its rugged landing gear and systems layout directly to Hellcat lineage. Each part designed to be replaced by hand in the field, each bolt accessible with one wrench size. Japan, studying the same data from the other side, drew different conclusions. At the newly formed Technical Research Institute in Mitaka, Tokyo, former naval engineers debated a question that haunted them. If America could outbuild Japan in 1945, how could Japan ever compete again? Their answer was stark, not by copying but by surpassing. Not in power but in precision. That idea, the pivot from imitation to innovation, would define Japan's technological resurrection in the 1950s and 1960s. The blueprint of defeat became the seed of rebirth. Tokyo, 1947. The war was over, but Japan's engineers had not disappeared. Their hangars were gone, their arsenals dismantled, their tools confiscated, but their notebooks survived. Among them, Commander Eiichi Iwaya, the man who had dissected the F6F Hellcat. He now worked at a modest research facility outside Mitaka, under the Aeronautical Research Institute of the University of Tokyo. The Allied occupation had banned aircraft production. The sky was closed to Japan. Yet every morning, Iwaya and a handful of surviving engineers gathered in an unheated wooden lab to do the only thing they knew, study. They called it Kagaku no Korigusa, the leftover weeds of engineering. Their purpose wasn't to build planes. It was to rebuild knowledge. The American ban was absolute. Since 1945, the Supreme Commander for the Allied Powers, SCAP, had prohibited the design or manufacture of any aircraft or engines. Machine tools were scrapped. Factories that had once built Zeros and Shurdens now made bicycles and cooking stoves. Mitsubishi Heavy Industries became Mitsubishi Machine Works. Nakajima Aircraft was reborn as Fuji Sanjo, building bus chassis. But beneath that economic rubble, a quiet intellectual network formed. Former Navy engineers, university professors, metallurgists. They studied old test data, including the translated F6F report that the Americans had returned for educational use in 1947. Ironically, the document written to understand an enemy aircraft now served as a textbook for rebuilding Japan's industrial base. At the University of Tokyo, Professor Hideo Itakawa, once chief aerodynamicist of the Nakajima Ki-84 Hay-8, began teaching applied aerodynamics using the Hellcat's wing profiles as case studies. He emphasized airflow control, lift coefficient management, and manufacturability. Students learned that an aircraft's success came not from perfection, but from reproducibility. The same principle guided Japan's post-war manufacturing revival. In 1948, former aircraft engineers joined Toyota, Nissan, and Hitachi. They applied assembly discipline learned from wartime aviation, tight tolerances, process charts, and quality tracking, to civilian products. When a young engineer named Taichi Ono developed the Toyota production system in the 1950s, he drew from aircraft assembly logic, small batch precision, continuous feedback, and error-proofing. It was aviation efficiency reborn as industrial philosophy. And at its root lay the hard lessons of the Hellcat. By 1950, when the Korean War broke out, the ban on aviation research was lifted. The U.S. Air Force needed maintenance support in Japan. The dormant facilities at Tachikawa, Nagoya, and Hamamatsu reopened under American supervision. Engineers who once studied how to destroy U.S. aircraft were now repairing them. In 1952, Fuji Heavy Industries, successor to Nakajima, was contracted to overhaul F-86 Sabres for the U.S. Air Force. Iwaya's former subordinates worked on the project. They were astonished by how much the Sabre system's design echoed the same modular, maintainable philosophy they had admired in the Hellcat. It was continuity through technology, a lineage of American engineering Japan could now study legally. The experience reshaped them. The engineers realized that the future wasn't about catching up in horsepower or speed. It was about precision manufacturing, process control, and reliability, areas where Japan could excel even without vast natural resources. By 1955, Japan's first post-war aircraft, the Fuji T-1 jet trainer, took shape. Its designers, many veterans of the Hellcat study, used American-style modular layouts and standardized fasteners. It was the first jet fully built in Japan since the war's end. Test pilot Kenichi Yoshida later said, "It was not built for war. It was built to prove we could build again." The symbolism was deliberate. The T-1's design borrowed aerodynamic cues not from the Zero, but from the F6F. Wide landing gear, sturdy undercarriage, and emphasis on pilot protection. It was in spirit a peacetime Hellcat. By then, Iwaya was an old man. He rarely spoke publicly, but in a 1956 interview with Asahi Shimbun he said quietly, "The Americans taught us without intending to. Their airplanes were our teachers." The lesson was that technology obeys discipline, not pride. It was the philosophy that would power Japan's next industrial miracle, from automobiles to cameras to electronics. The same men who once failed to copy a Hellcat now built machines the world would one day copy from them. Bethpage, New York. 1958. Inside Grumman Aircraft's engineering hall, the blueprint for the F-11F Tiger lay on a drafting table, a sleek, supersonic descendant of the F6F Hellcat. Next to it hung a photograph taken 13 years earlier, a bullet-riddled Hellcat on Tinian Beach, 1944. Beneath it, a brass plaque read, "Toughness wins." For the Americans, the lesson of the Hellcat had matured into doctrine, durability, standardization, pilot protection, and logistics superiority. These weren't just design philosophies, they were principles of national defense. Each Grumman aircraft, from the Bearcat to the Tiger to the future F-14 Tomcat, was built around those same core ideas. Meanwhile, 6,700 miles away, those same ideas were being reinterpreted in Japan. Tokyo, 1959. In a clean, sunlit laboratory at the National Aerospace Laboratory of Japan, NAL, a group of engineers studied stress data from the Fuji T-1. Among them was Hiroshi Iwaya, son of Commander Eiichi Iwaya. He had joined NAL as a structural analyst, working on aluminum fatigue testing for jet fuselages. On his desk was a worn copy of his father's wartime notes, the F6F load distribution tables. To him, those figures weren't history, they were foundations. By the late 1950s, Japan's aerospace revival was fully underway. Mitsubishi Heavy Industries, Fuji, and Kawasaki had signed agreements with Lockheed and North American Aviation. They began licensed production of the F-86F Sabre, assembling over 300 units between 1955 and 1961. The precision that once eluded them now defined them. Each bolt torqued to exact U.S. standards. Each panel gap measured with imported feeler gauges. The American engineers overseeing the program remarked that Japanese tolerances were within 0.001 inch, better than U.S. Navy spec. The student had surpassed the master's patience if not yet his reach. But the true shift wasn't mechanical, it was philosophical. Japan no longer chased speed records or dogfight agility. They pursued reliability, efficiency, and process control. It was the Hellcat doctrine translated into peacetime industry. At the same time, the United States was drawing a different conclusion from the same lineage. Jet-age warfare demanded reach, not just toughness. The Navy's doctrine evolved into carrier power projection, a global logistics machine built on lessons learned from the Pacific. The Hellcat had proven that logistics could win wars. Now jets like the F-4 Phantom would prove that range and integration could hold peace. And yet, at their core, both nations were walking parallel paths born from one airplane. In 1962, Japan introduced its first jet interceptor, the F-104J Starfighter, built under license from Lockheed. It was a radical leap, Mach 2 titanium skin, razor-thin wings. But the engineers who assembled it came from the same generation that once studied the Hellcat wreck at Yokosaka. They remembered the lesson: maintainability saves lives. So they modified wiring harnesses, simplified access panels, and reinforced gear struts for Japan's humid climate. Lockheed engineers later admitted the Japanese-built F-104JS were the most precisely assembled starfighters in service. Technology had become doctrine. Not the dogma of national pride, but the discipline of continuous improvement. Across the Pacific, Grumman engineers were drawing plans for the F-14 Tomcat, the ultimate carrier defender. Its variable sweep wings, twin engines, and heavy armor made it the spiritual heir to the Hellcat. The same core tenets persisted: protect the pilot, build for abuse, win through engineering. And in both nations, separated by history and war, the philosophy had converged into a quiet truth. The winner of the Pacific Air War wasn't just the side with better pilots or faster planes. It was the side that mastered systems. The Japanese engineers who once reverse-engineered the Hellcat understood that too late. But their children built an industry on that revelation. An industry that, within a generation, would power not just aircraft but automobiles, ships, and electronics that would dominate global markets. From the wreckage of 1944's Tinian Beach to the jet lines of 1960's Nagoya and Bethpage, the Hellcat's shadow stretched long. A single airplane had reshaped how two nations thought about machines, men, and mastery. Bethpage, Long Island, July 1976. The last F-14A Tomcat of that production block rolled off the Grumman line. Engineers applauded quietly. No speeches, no banners. Just the rhythmic sound of wrenches being set down. The same ritual as 1943 when the first F6F Hellcat had left the same floor. Grumman's chief historian, Bob Wood, kept a small display beside his desk: a fragment of an F6F cowling, a Pratt & Whitney spark plug, and a copy of the Japanese Technical Analysis Report, Model F6F5. He called it the enemy's complement. Every new engineer was shown that report during orientation. A reminder that every bolt, every weld, had once been measured by men who fought to destroy it. Half a world away, in Nagoya, Japan, Mitsubishi Heavy Industries was assembling the F-1, Japan's first domestically designed supersonic fighter. It flew for the first time on June 3, 1975, 31 years after Japan surrendered. Its engineers were descendants, literal and professional, of the men who had once catalogued the Hellcat. The F-1's aluminum alloy composition, modular access panels, and redundant hydraulics all traced conceptual ancestry to the very aircraft their fathers had studied in the ruins of 1944. History had inverted itself. The imitators had become innovators. In 1977, an American aviation delegation visited Japan to observe Fuji Heavy's production of the T-2 trainer. Among the U.S. guests was retired Rear Admiral Frank McIntyre, the same officer who, in 1945, had recovered the Hellcat report from Yokosaka. Now in his 70s, he watched Japanese technicians assembling components with digital torque tools, laser alignment systems, and process charts cleaner than anything he'd seen at Grumman. He turned to his host, a quiet engineer named Hiroshi Iwaya, son of the man who'd written that original report. "You know," McIntyre said, "your father's work helped us understand how you thought. Looks like you used ours to figure out how we think." Iwaya smiled faintly. Then perhaps both sides finally learned the same thing: machines are honest teachers. By the 1980s, Japan's aerospace industry had become a global supplier of precision components for Boeing, Lockheed, and Airbus. The country that once struggled to copy a Hellcat was now machining wing spars for the 747 and composite panels for the F-15J Eagle. Its manufacturing accuracy, measured in microns, was the quiet echo of lessons written in fire and defeat. And at Grumman, the Tomcat continued the Hellcat's legacy, not in shape but in spirit. Rugged, reparable, built to protect its pilot above all else. It was the doctrine of practicality, the worship of reliability. The Hellcat's DNA still lived in its hydraulic redundancies, its massive landing gear, its armor around the cockpit. In 1986, when Top Gun made the F-14 an icon of American power, few remembered that its lineage began with a crash on a coral beach 4 decades earlier. Fewer still knew that deep inside Japan's archives sat a single surviving volume, bound in gray cloth, marked Gokuhi. Its pages yellowed, its diagrams still sharp. A record of engineers who tried to catch up and instead discovered something larger than imitation, the logic of progress itself. On its final page, Commander Eiichi Iwaya had written in neat, formal characters. Superiority is temporary. Understanding is permanent. That understanding, forged from wreckage and reverse engineering, from failure and fascination, had bridged 2 former enemies and quietly redrawn the map of industrial civilization. The F6F Hellcat was never just an airplane. It was proof that war, for all its destruction, could sometimes teach nations how to build peace.